Hey, what's up, everybody? This is Sean Downs, Sean for Science from the Pasayten Institute, and today I'm here to talk about inner products of vector spaces. So last time we kind of dug into the nuts and bolts of what made up a vector space, thinking about it in terms of modules over some ring, and today we're going to do a bit of the same. First off, though, let's talk about real vector spaces. We put inner products on vector spaces for all kinds of reasons. Typically we want to be able to compare vectors against each other through some kind of projection operation, or maybe we want to have some kind of normalization to go with those vectors. But ultimately, all of these things are there specifically to define a concept of distance on our vector space, because we want to do calculus with those vectors. So to accomplish this, at least with real vector spaces, things like r to the n, we usually call upon a symmetric bilinear form, or, a dot product. So let V be a real vector space, and let's use angle brackets to represent a symmetric bilinear form that takes the Cartesian product of V times V to the reals. To function as an inner product, we demand that the diagonal values of that form restrict to the positive real numbers. N vanishes only for the zero vector. So the prototypical case for this is inspired by the Euclidean distance function on Rn. So if x is a vector in Rn with components x sub I, the bilinear form x with x equals the squared sum of the components. And this implies that, for y also in Rn, different from x with y may be 0 or even negative. Nevertheless, the symmetric bilinear form induces a distance function on Rn, d of x, y, defined as the self-product of the vector x minus y. To prove that d is a distance function, we typically need to verify three things. First, that the distance function vanishes if and only if the vectors are the same. Two, that the distance function is symmetric. And three, that the distance function satisfies the triangle inequality. So for the inner product modeled by the Euclidean distance function, this is pretty much built in by design, but generally speaking, one follows from linearity and demanding that the positive definite nature of the vector's self-product holds. Two, symmetry follows from the symmetry of the form, of course. And three, follows from both one and its logical antecedents. So when a real vector space V is equipped with such a distance function induced by the symmetric bilinear form, and that space is complete as a metric space, like in the Cauchy sense, say, then we call V a real Hilbert space. And Hilbert spaces are of interest, of course, because we want to do calculus with them. Now, unfortunately, this construction doesn't survive generalization to more complicated scalar fields. So, for example, let W be a complex vector space. A symmetric bilinear form on W fails to provide a distance function. To see this, it suffices to consider the complex plane itself. Let Z be a complex number, say A plus IB. A symmetric bilinear form on C would give you, Z with Z being A squared minus B squared plus 2IAB, which isn't real, one, and it can be negative, of course, for, say, A equal to 0. But, you folks are no fools. You know how to extract the Euclidean distance function on C. You got to take Z times Z bar. That is the complex conjugate. But immediately we see that we lose the symmetric nature of the bilinear form to accomplish this. So a more general discussion of inner products on vector spaces typically demands three axioms that are given in terms of, say, one, linearity on one side of the form, whatever it is. Two, that form satisfies some kind of hermiticity condition. And three, that form is positive definite. Yeah, but these axioms are, from my perspective, tremendously sterile. Like, I don't have any intuition for what it means at all or where they come from. It's kind of replaced the bilinear symmetric form, which is something that's kind of nice with this weird linear antilinear condition. And positive definiteness is typically depends on the hermiticity, that conjugate nature itself. So in some sense, that hermiticity condition kind of dominates the other two. So is there a better way to understand where all of this comes from? Well, personally, I'd like to think so. So what are we even doing here with an inner product? An inner product on a vector space is a map ostensibly a linear map from the Cartesian product of that vector space with itself into the underlying ring of scalars. So like V cross V into R, the reals, or W cross W into C, the complex plane. And we want to do this in such a way that calculus makes sense. We want to build a Hilbert space. That's really what we're after. So as we've seen from studying the more complicated scalars like the complex plane, or more generally other division rings, that Cartesian product just isn't good enough. We need to inform that product somehow of the algebra latent in the scalar field. We need to teach that Cartesian product of vector spaces about the conjugate scalars. And it's that kind of conjugation that gives us the Euclidean distance function after all. So how can we wrap that algebraic idea of conjugation into that kind of set theoretic idea of Cartesian products? So how can we model this idea? Well, let's recall our discussion from last time and kind of generalize to the case of modules and rings. So let R be a unital ring and let M be a unitary left R module. You might recall that M is actually an abelian group that got upgraded to a module by the ring action of what we called scalar multiplication last time. Of course, we have in mind that M is actually a vector space and R is actually a ring of scalars. But let's proceed at this level of generality anyway. So R has a natural sense of duality associated with it. Namely, for each ring R, there is another ring, the opposite ring, and a natural ring isomorphism between them that essentially just kind of switches out left and right multiplication. For the module M, that isomorphism induces a ring module isomorphism that's also pretty natural. So M is taken from like a left R module into a right R module under this action. So now, what if we want to do something sneaky? Remember, we're trying to inform the Cartesian product about the conjugation of the algebraic scalar. So what if we augmented that natural isomorphism, that left-right isomorphism, to include the conjugate map of the scalars? So as it turns out, there's already a technology built around these ideas. So suppose the unital ring R has an involutive automorphism. That is to say, a ring automorphism that squares to itself. I.e., suppose it's a star ring. So a star ring has some additional properties and consistency requirements, like the multiplicative unit is invariant under the involution. But the weird one is that the involution of a product is the reversed product of involutions. Now, why would you do that? Well, let's hold that thought and go back to our module M for a second. So consider the Cartesian product of M with M, which is supposed to model our Cartesian product of vector spaces W with W, the domain of the inner product. So let's twist that product M with M a little bit and let one of those factors be a left R module and let the other one be a right R module. In other words, we're going to apply that opposite module isomorphism we discussed earlier to one of the factors. Now, we can then form the tensor product of these two modules, which essentially mandates some consistency requirements for pairs of items that come from the two and how their multiplications interact. That comes in the form of a conditions for something that's called a middle linear map. The conditions are here. Fortunately for us, there is a canonical choice of a middle linear map in this case, and thus it's a very natural thing to discuss, technically speaking. Call this tensor product module something cute, like MM. So MM is now an R bimodule, which means that we can dispense with all the worries about bilinear maps and just focus on the linear ones from the bimodule to R itself. Of particular interest here is going to be a different middle linear map from MM to R. And this different middle linear map is going to be the prototype for our inner product of vector spaces. And this is where we're going to call in our demand for R to be a star ring. So let's combine the opposite map, the opposite ring map, with this star, that involution on the ring, the conjugate if you like, and push that combined map forward through the ring action that defines the opposite or right R module, which we'll now call M star. So now we have the bimodule M star. Specializing briefly to the case where W, a finite dimensional complex vector space, is M, and R is the complex numbers, we see that the Hermitian inner product that you normally would define on a complex vector space defines a middle linear map in the requisite way. Note also that this construction applies to the non-commutative case. So for so-called left vector fields defined over division rings, like, say, the quaternions, actually, that funny reverse multiplication rule in the definition of a star ring is actually designed precisely with the non-commutative case in mind. Once again, revealing how the algebraic structure of the underlying ring of scalars ultimately is what defines our notion of a joint or conjugate relative to the inner product of vector spaces. Incidentally, this construction also makes things like operators and their associated adjoint operators, like taking transposes and conjugates and whatever, their crazy anti-linear behavior of Hermitian conjugates, generally speaking, makes it feel a whole lot more natural, or at least we can get a sense from where these ideas are coming from. At least I think so. So for finite dimensional vector spaces, this idea helps us understand the whole construction of duality, the whole idea of a dual space. Sure, a lot of folks are going to define a dual space in terms of the set of linear maps from a vector space into the underlying scalar fields and pretend like that's the most natural thing to do and it's obvious and whatever. And I think that's crap. No, it's not. But for now, anyway, for the finite dimensional case, we can talk about duality as being related to the construction at the level of the binary operation of ring multiplication and flipping left and right, which feels a whole lot more natural to me, both technically and informally speaking. Incidentally, this also highlights the difference in perspective of the construction of a dual space for infinite dimensional vector spaces, and maybe why topological vector spaces might prefer to think of duality in terms of continuous or linear continuous maps as opposed to kind of the underlying ring multiplication. But that is an analysis discussion, and that is a discussion for another time. That's all for today. These are just my humble opinions on how inner products should be thought of. Thanks so much for watching. See you next time.